Okay, Assalamualaikum and good morning. Okay, so this is our final chapter for MEC251 internal combustion engine, and this is the recorded video, and I try to finish this chapter in this video. If not enough time, maybe I will continue into another video after this. Okay, so internal combustion engine, I think most of you have already heard about this. The common applications here is the engine in the car, in your car and your motorcycle, and most of the road vehicles we still using the internal combustion engine, but in the future maybe it will be replaced by the electric motor. That's what we call the EV, electrical vehicle. But for the time being, majority of the transport in the world still using the internal combustion engine. So this topic is still relevant to our real life. Okay. So the history of the internal combustion engine started from the Otto findings. This is the Nikola Otto, a German, in 1876. Okay, so what he found that the system of engine that use of two processes. One is the isotropic processes and the constant volume processes. Okay, so if you want to know a little bit or refresh back what you have already learned about the internal combustion engine, you can click on this link here, and it will be redirect to the YouTube, and you can see by your own 3 minutes video here. Okay, and then I will try to explain you based on the TS and PV diagram here. Okay, so for the TS diagram, for the Brayton cycle before, we have the pressure constant, but for the internal combustion here, Otto cycle here, we analyze the system based on the constant volume. Okay, this is because we have constant volume process instead of constant pressure process as we found in the Brayton cycle in the previous chapter. But for the Otto cycle, we have constant volume process. So the other things are quite similar to the Brayton cycle, but just the difference here is the constant volume instead of constant pressure. Okay, so keep it in your mind. We have constant volume for the Otto cycle, and for the Brayton cycle we have constant pressure. Okay, so for the TS diagram here, the first state 1 to the state 2, similar to the Brayton cycle before, we have the isentropic compression. Okay, and then the heat addition here, okay, goes into the system from the state 2 to the state 3, still similar to the Brayton cycle. Okay, but instead of pressure constant in the Brayton, we now are facing the constant volume here. So please memorize here, state 2 to state 3 is the constant volume heat addition. Okay, heat addition because of the Q in here. And then from 3 to 4, similar to the Brayton cycle before, we have isentropic expansion there. This is the process that produce the work out, and then finally you have to exhaust, or you have to reject heat outside. So similar to the Brayton cycle, okay, as we found in our car engine, so we just remove the Q out, okay, by using the exhaust. Okay, as you see at the back of your car, there is an exhaust pipe. So there is an exhaust pipe that reject heat to the surrounding, so the temperature will goes down back to the original state. Okay, so means the original state here is the air intake that goes back into your engine, and the cycle will goes continue looping the cycle until you shut off you shut down the engine. Okay, so quite similar to the Brayton cycle, but just the volume constant process here between 2 and 3 and 4 to 1. Okay, so let's refresh back a little bit of the 4-stroke combustion engine here. The first one is the isentropic compression, where the piston will compress the air, okay, from state 1 to state 2. This is the isentropic process from state 1 to state 2. And after you compress, okay, so the combustion will happen here, where the air fuel mixture will be ignited by the spark plug, okay, and then the combustion will be happen. It's like a detonation lah, meletup. Okay, and then when you have the combustion here, the energy there will push the piston down, okay, as we see here in the isentropic expansion. So during the state 3 to state 4, there will be work output during this process. And finally, it will goes back to the from state 4 to the state 1, where the piston push back the gas that is produced by the combustion process. So here we have CO2, CO, carbon monoxide, and maybe some of nitrogen dioxide and so on. Okay, so it will be reject to your exhaust. Okay, so basically there is our principle of the Otto cycle. So what you have to remember here, the TS diagram and PV diagram. So 1 to 2 is isentropic, 2 to 3 heat addition, constant volume, 3 to 4 isentropic expansion, and 4 to 1 constant volume heat rejection. So similar to the Brayton cycle, just you will change the pressure in the Brayton into the volume here for the Otto cycle. Okay, so if in the Brayton cycle we have the pressure ratio, which is the P2 over P1 or P3 over P4. Okay, that is the Brayton cycle. But for the Otto cycle here, internal combustion engines here, we have the compression ratio. Okay, the compression ratio is the V1 over V2. Okay, the symbol here is RV. Pressure ratio is RP. P pressure, V volume. Okay, and then our thermal efficiency, still you just have to remember this one. And our Q in, okay, different compared to the Brayton cycle, because of right now we have the constant volume. Okay, constant volume, so you have to use the CV instead of CP. Okay, because we know that CV is the specific heat capacity at constant volume. So because we have the constant volume process, so we have to use the CV, bukan CP, not CP but CV. So the T3 minus T2 is quite similar lah. It depends on the temperature where the process occurs. So the combustion or Q in here happen between the 2 and 3, so temperature 3 minus T2. So your Q in here will be CV because constant volume. Okay, temperature 3 minus temperature 2. How about the Q out? Similar, Q out. We have to use the CV because of constant volume. T4 minus T1. Okay, so beza okay, difference. Kalau Brayton cycle we use the CP because constant pressure in the Brayton cycle. But for the Otto cycle we have the constant volume, so we must use the CV, constant volume. Okay, so quite straightforward here. The thermal efficiency here, so never mind, you just have to remember here thermal efficiency is the W net over Q in, and the W net for the Otto is Q in minus Q out, still the same as the Brayton cycle. Okay, so the Q in here is the CV T3 minus T2, and Q out here is the CV T4 minus T1. But honestly, you don't have to remember the Q in and Q out. You just have to understand the TS diagram here. So you just have to know where is the process of Q in, where is the process of Q out. That's it. So you just derive your equation there for the Q out to find the formula there. Just you see what temperature involved here. So the T4, temperature 4, and temperature 1. So that is the Q out. And for the heat addition, Q in, so you see here, you put it number 3 here, so it is a state 3, and this is the state 2, so temperature 3 minus temperature 2, and you have to multiply with the CV because this is the constant volume. Okay, so the other thing is you have to know the formula for the isentropic process. Okay, why? Because we already derived here before. We have 3 types of isentropic formula, isentropic process. So we have to choose which one to be used in this Otto cycle. So it is related to the volume and the temperature. So we have to use this formula for the Otto cycle, and also in the internal combustion engine lah, in general. Okay, so this one, so make sure you have to use this one for the isentropic process. Okay, where is the isentropic process? You see back to this slide, we have 2 isentropic process here, between 1 and 2, which is the compression, and 3 to 4, which is the expansion, same as in the Brayton cycle before. So if you understand the Brayton cycle, the Otto cycle is quite easy for you. Okay, we have to use that formula, T2 over T1 equal to V1 over V2 K minus 1, right? K minus 1. So we see that I double check. Okay, 2 minus 2 over T1, V1 over V2. Okay, correct. 2 over T1, V1 over V2 is the to the power of K minus 1. You have to use only for the isentropic process, state 1 and state 2, and the other one is the isentropic expansion process between the state 3 and state 4. So you have to use T3 over T4 equal to V4 over V3 K minus 1. So only use for the isentropic process. Sama juga dengan Brayton cycle sebelum ni, gas turbine tu sama juga, kita boleh pakai waktu isentropic saja. So formula ni hanya apply untuk isentropic. What if you use this formula for the state 2 and state 3 process? It's totally wrong. Okay, tak boleh pakai rumus ni. Yang ni nak pakai rumus mana? Yang ni kita pakai macam biasa, P1 V1 over MRT1 equal to, ni P2 lah, P2 V2 over equal to P3 V3 over MRT3. So since as same mass and gas constant, you can simplify it to this one. Okay, and then we have another relationship here. The volume is constant, so V2 over V3, because it is constant, so it has the same value, so you can cancel V here from this equation. So this one can be used for the state 2 and 3, and also state 4 and state 5. State 4 and state 1, 5 plug. Okay, this one. Okay, so that's all to get the temperature value, because that is our ultimate parameters that we have to find before we can calculate our thermal efficiency. Here you see there we have to use the temperature, because we only have to find the temperature. And how about the value of the CV? CV is given, will be given in the test question and also the final question. Okay, so another parameters that you have to find is also the MEP, mean effective pressure. So before, in the Brayton cycle, in the gas turbine, we have to calculate the work ratio, back work ratio, and so on. But for the internal combustion engine, we do not need to calculate the work ratio. We have another parameter that we have to find. It is called the mean effective pressure, MEP. Okay, so since it is a pressure, the equation here, P times V is, if you still remember, equal to work PV equal to work. So here effective pressure, PM here symbol, times with the V1 minus V2 will be equal to W net. Okay, and then you rearrange the W net over V1 minus V2. Okay, so I just want you to remember until this also. Okay, but if you substitute here RV, since RV equal to V1 over V2, so you can substitute into this one, so you will get final formula there. But for me, you remember this one or this one is also okay. So that's the parameters that you have to find, basically similar to the Brayton cycle. Normally we start with the temperature, so we have to find temperature 1, temperature 2, temperature 3, and temperature 4. Okay, after you have this temperature, you have to find the thermal efficiency is equal to W net over Q in, which is Q in minus Q out over Q in. Okay, so to find the Q in, you use the formula of CV, T3 minus T2, and Q out is CV, T4 minus T1. So you have this value, and you will get the thermal efficiency. Okay, and normally in the test or in the final test, you also will be asked to find the PM. Okay, what is the PM? Mean effective pressure. So PM equal to W net over V1 minus V2. Okay, so after you get the value W net, this one, Q in minus Q out, so you have to find the V1 and find the V2. So since we have the RV normally will be given, must be given in the test or in the final, must be given in the question. So RV equal to V1 over V2. So you have to find the value of V1 and also value of V2. So you put that value into this formula, you will get the PM. PM must be in the unit of kilopascal. pressure must be in the unit of kilopascal. Okay, so basically that is the flow how to calculate this question regarding to the Otto cycle. Okay, so that's it for now. And then after we try these examples, I will go more into the diesel cycle and the dual cycle. Okay, diesel and dual is just the continuation research after the Otto cycle. So basically diesel cycle is the principle or the system that is used in the diesel engine that you found in the cars, in the truck, in the lorry, in the bus, and so on. So quite different, but still similar to the Otto cycle. And finally, we also have the dual cycle. Okay, this one. So don't worry about that. Just to give you general info, the final test and the final and the test 2, mostly the question will ask you about the diesel and dual cycle. So to this date lah, we never have the question about the Otto because Otto is so simple. Normally you will be asked about the diesel and dual cycle. Okay, so let's try this example from the textbooks. I will show you. The answer here is already given because this is the question in the textbooks, but I will show you how to calculate one by one. Okay, so stay tuned. Okay, example 9.1 and 9.2 from the textbooks. An ideal Otto cycle has a compression ratio of 8, so RV here is 8. At the beginning of the compression process, okay, before that, to make it easier for you to understand the question, I very highly recommend you to draw a TS diagram first. Oh, sorry. TS diagram. So you will just have two lines of volume because this has a constant. So this is the state 1. You will have the constant isentropic process, compression process from the state 1 to state 2, and you have constant volume heat addition until the state 3, and you have isentropic expansion 3 to 4, and finally heat rejection constant volume. Okay, so at the beginning of the compression process, cause a compression here between 2 and 3 is the compression. This is the heat addition. Dapat D, heat rejection 4 to 1, and 3 to 4 is the expansion. Okay, so the meaning of this sentence at the beginning of the compression process, so means that air is at 100 kPa here, means the state 1. So you just write down state 1. The value here is P1 equal to 100 kPa, and 70 degrees Celsius is also about the beginning of the compression process. So this is the temperature 170 degrees C. When 800 kilojoule per kilogram of heat is transferred to air during the constant volume heat addition process. Okay, which one? Between the 2 and 3 heat addition. So you put it there, 800 kilojoule per kilogram, the Q in. So the value of Q in is already given, 800 kilojoule. Okay, so I put it here, state 2, state 3, state 4. So we put it the information here. 800 kilojoule is the Q in, so yeah, I put it here. Q in is 100 kilojoule per kilogram under the state 3. So you write down the equation for the Q in is CV T3 minus T2, right? Is equal to 800. Okay, and then okay, the original questions here the mentions here is the variation of specific heat. Okay, perubahan specific heat, but because of our syllabus only consider the constant specific heat. Sepatutnya in reality we have to consider the variation, because the specific heat will change depends on the temperature and so on. But in our syllabus, to make it simpler or also make it easier for you, we consider the constant specific heat only. So you just have to use one value of the specific heat only throughout the system. Okay, so in the end maybe our results will be different. Okay, we will have the different results compared to this answer from the textbooks, because the textbooks using the variation of specific heat, and my method here will show you the methods that use the constant specific heat. So our final answer will be different lah compared to this one. So never mind, don't worry about that, just stick to my methods for your syllabus. Okay, and then what we are going to find is the number A is the maximum temperature. Okay, which one is the maximum temperature? Similar to the Brayton cycle, the Otto cycle also, the highest temperature is before the expansion process. Okay, so it is the state 3. So we are going to find the state 3. And B, you have to find the net output, so W net. So I just put it here, Q in minus Q out. And C, thermal efficiency. You see there? That's what I have mentioned earlier. We have to find the temperature, we have to find thermal efficiency, and before thermal efficiency we have to know the W net and so on. So similar kan? So this is the normal questions for the auto or and also internal combustion engine. Okay, so this is normal question that you have to be very familiar about this. Okay, and finally D, you have to find the MEP, main effective pressure, PM lah. So PM is equal to W net over V1 minus V2. Okay. Okay, so make sure you put it here. Isentropic is between 1 and 2, and another one is between 3 to 4 isentropic. Okay, so between state 1 and state 2, we have another one is the RV. RV is 8. RV is also equal to V1 over V2 equal to 8. Okay, you see there, V4 over V3 is equal to equal to 8 RV. Okay, and then we have to use our isentropic formula between the state 1 and state 2, which is T2 over T1 equal to V1 over V2 K minus 1. So the K here for the air still 1.4, and after that T2 times T1 V1 over V2 K minus 1. So you will get T1. You have to convert into the Kelvin. So 273. you will get 290, right? So 290, V1 over V2 is 8, K minus 1 is 0 0.4, 1.4 minus 1 is 0 0.4. So your answer for the T2 will be sorry, this one is V2 over V1 equal to 8, so it be 1 over 8 lah. Okay, so you will get 1, right? Okay, I just check first. Compression ratio of it. T2 over T1, V1 over V2. Alright. So R. V1 over V2. Okay. So this one will be okay, 6.24 Kelvin. Okay, correct. And then we have the T2 there. So we are going to use this value there to find our T3. So CV T3 minus T2 will equal to 800. So T3 will be 800 over CV. CV is 0.718 for the air. So if you don't have that value, don't worry. You can see here in the past year question, CV is given, okay, 0.718 for the air. That value is for the air. So here is the air. And then we use 0.718 for the CV value, and then T2 will be there, will be plus. T2 is 6.24 Kelvin, and our answer will be, I try to use 800 over 0.718 plus 666.24. So our value is 1700 Kelvin. So I just stick to decimal places. Yeah. So this is our temperature for the T3. And finally, we have to find the T4. So between the state 3 and state 4, we also have the isentropic process. Yang ni kan, between 3 and 4, expansion ni isentropic expansion. Ni isentropic compression. So we can use this formula. So the T4 over T3 will equal to V3 over V4 K minus 1. So T4 will be T3 V3 over V4 K minus 1. So T3 here is 1780.45. V3 over V4 is the reverse of the RV, so it will be 1 over 8. 1 over 8. So 1.4 minus 1, and your T4 will be 1784.45 times with bracket 1 over 8, the power of 0.4 close bracket equal to 77 Kelvin. So I will take decimal places. So T4 will be 774.99. Okay, so we have everything. We have the temperature for every state. So T1 is 290 Kelvin, T2 is 666.24 Kelvin, and our T3 is 1780.45 Kelvin, and finally our T4 774.99 Kelvin. So after we have all those value, we can now calculate our W net. So our B, this is our answer for this is, T3 is our answer for the A questions. Quite different, right, compared to the answers in the textbooks, because the textbooks use the variation of specific heat, but for our syllabus we use the constant specific heat. Okay, CV there. Okay, so B, we have to calculate the W net. Okay, W net for the Otto cycle also is equal to Q in minus Q out. So our Q in is between the constant value state 2 and state 3. So our Q in will be CV T3 minus T2 minus Q out CV. Also for the Q out is between the state 4 and state 1. So it will be the T4 minus T1. So you put it 0.718. T3 is 1780.45 minus T2 666.24 minus 0.718. T4 774.99 minus T1 290. So our W net, because we don't have mass in front of the CV, so our unit will be in the kilojoule per kilogram. Yeah, our answer is A. Okay, it's wrong if you have the negative value. Q in minus Q out. Q in 3 2 2 6 6 6. Okay. So our W net is 451. Okay. Quite far off compared to the answer from the textbook 418. We have 451. So never mind. Just stick to my method. Just follow my method. So thermal efficiency, the number C, you have to find thermal efficiency. So thermal efficiency is W net over Q in. So you already have the value here, 451.78. So we just have to calculate this one lah, Q in. So 0.718 times 1780.45 minus 666.24 times 100%. So our thermal efficiency is 56.47%. So that's your answer. And finally, you have to calculate the MEP, mean effective pressure, symbol of PM equal to W net over V1 minus V2. Okay, because of W net here is in the unit of kilojoule per kilogram, so here V, you also have to use the meter cube per kg, the unit there. Okay, okay, so if you want to use the RV value, so RV equal to V1 over V2. So I will just replace the V2 there. So V2 will be equal to V1 over RV. So the PM will be W net over V1 minus V1 over RV. Okay, so right now we only have to find the V1. How to get the value of V1? We can use the equation, either gas equation, PV equal to RT. Okay, and then to find the V1, so you will get the V1 equal to RT1 over P1. Okay, so right now we have to use the parameters of temperature and pressure at the state 1. So state 1 we have 290 for the temperature, and for the pressure we have 100 kPa. So 100 times 290, oh sorry, that is the R. R is also will be given in the question. So let's see the pass here. R for the air is 0.287, so you are going to use that value 0.287 Okay, this is given, the value is given. Okay, times with the temperature of T1 290 Kelvin over P1 is 100 kPa. Okay, so your V1 will be 0.287 times 290 over 100. So you will get 0.8323 meter cube per kg. Okay, use this formula, this value, so you have to substitute in this formula, so you will get PM equal to W net. We already have that value, 451.78 over V1, 0.8323 minus V1, 0.8323 over RV. RV is 8. So your mean effective pressure will be equal to it's 0.35 kilopascal. So that is our answer. Okay, so you see there, our value here is different because of our work net is different. Okay, so that's all for the example 9.2. Okay, so let's go to the diesel cycle. Okay, I already put a link to the YouTube video that explain what is the difference between the Otto cycle, gasoline, and also the diesel cycle. So in the diesel cycle, instead of we use the constant volume during the heat addition here. Sorry. Okay, we have both constant volume for the heat addition and constant volume for the heat rejection. This is the Otto cycle. But for the diesel cycle, they change a little bit at the heat addition. It use the constant pressure, this one, during the heat addition, Q in, and they use the constant volume during the heat rejection here. So instead of CV there, here we are going to use the CP. So this is the diesel, so that's the difference between diesel and Otto. Q in will be CP because the pressure is constant, so CP T3 minus T2. And for the Q out, still the same as the Otto cycle, we have to use the CV because of the constant volume. Okay, and the PV diagram here, you will get constant pressure there during the okay, before that, for the Otto cycle, okay, we have constant volume. Okay, this one is Otto. This one is diesel. You see the difference there between the Q in. Okay, so 1, 2, 3, 4. Okay, so the difference here between the Q in the diesel, we use the constant pressure because we don't have the spark plug in the diesel cycle. The ignition naturally happen during the compression process, so that's why the pressure there is constant. So different there between the auto is gasoline, the normal engine that we use here, petrol, gasoline petrol. Okay, this one is the diesel. So the difference here between the heat addition. So during the diesel we use the constant pressure, during the auto we use the constant volume, and for the heat out still the same, we use the constant volume. Okay, so the other thing are quite similar, but we have another term for the cut-off ratio. So before that we have the RV, which is the compression ratio, which is V1 over V2. We call it compression ratio. For the diesel, we have to use to get the cut-off ratio. The symbol is beta because this one only refer to the constant V3 over V2 here during the constant pressure. Waktu constant pressure Q in. So waktu tu kita kena pakai cut-off ratio ni. Okay. Jadi saya akan tunjuk example ni. Okay, soalan past year, question 4, June 2019. Okay, so here is an ideal diesel engine with the maximum temperature of the cycle is 1500 Kelvin. So you see there the temperature 3 is 1500 degrees C. Designed to have a compression ratio of 18. So this is the RV. At the beginning of the compression process, the air is compressed at 20 degrees C. So at the beginning of compression is between the at the state 1 lah. So this one is the temperature 1. So pressure 1, 110 kPa. So the question here is the normal questions. You have to find the temperature, and extra answers you have to find is to find the pressure at every state. So we write down every state: state 1, state 2, state 3, and state 4. So we list down the information that we already have. The T3 is 1500 degrees C, equal to, you have to plus 273, so 1773 Kelvin. Okay, and then RV is between the state 2 and the state 1, so RV V1 over V2 is 18, and then we have the temperature 1, 27 degrees C, equal to 300 Kelvin, and our pressure 1 equal to 110 kPa. Okay, so the isentropic process still similar between the state 1 to state 2 and state 3 to state 4 isentropic. Okay, how about the state 2 to the state 3? It's not the constant volume anymore because this is the diesel engine. The diesel engine is the pressure constant happen between the state 2 to the state 3 process. So here is P constant. So you will get P2 equal to P3 lah, and P3 equal to P2. How about the state 4 to the state 1? You have the volume constant, so V4 is equal to V1. Okay, so that's all the information we have, right? RV here, constant. Okay, compression process here, it cannot be used anymore for the state 3 and state 4 because the state 3 is different. Okay, so the RV all only can be used between the state 1 to the state 2. So for the diesel engine RV here can only be used between state 1 and the state 2. Okay, so let's find the temperature and pressure at every state. So the T1 P1 already have, so that's okay. So we are going to find the state 2 here. So to find the state 2, the information to state 2 is we can use the isentropic formula. T2 over T1 equal to V1 over V2 K minus 1. So T2 equal to T1 V1 over V2 K minus 1. So you will get T2 equal to temperature 1 300 Kelvin times V1 over V2 is 18. K minus 1 1.4 minus 1 is 0.4. So our T2 is 953.30 Kelvin. Okay, so our pressure here, you can use PV equal to RT, but we don't have the volume, we don't have the volume, so we cannot find the P2, right? So that's okay. We can relate the state 2 and the state 3 is the P constant, so we can use this equation, ideal gas equation, which is P2 V2 over RT2 equal to P3 V3 over RT3. Okay, so P is constant, R can be neglected because it has the same temperature, and we already have the T2, we already have the T3, so now we can have the V2 over V3, which is we call the cut-off ratio here. So V3 over V2 is equal to T3 over T2. So our cut-off ratio equal to T3 1773 over T2 is 953.30. Okay, so just KIV first out to get the pressure. We try to find every temperature first. So P3 here, also KIV, we can use the okay, so for the T2 we can use our another formula for the isentropic process, which is equal to this one. We can use our another formula. Okay, right now we want to find our pressure, so we can use this formula, P1 over P2 over equal to V2 over V1 to the power of K. Okay, so because it is an isentropic process, we can use any isentropic formula that you want. So right now we want to find the pressure, so we can use the P2 over P1 equal to V1 over V2 the power of K. So we have already the P1, so P2 will be 110 times V1 over V2 is our RV 18, so K is 1.4. So your P2 will be 9291.79 kPa. So that is our P2, temperature 2 and P2. Okay, so P3 is also 9291.79 kPa. So we have already solved the pressure and temperature for the state 1, state 2 and state 3. And finally for the state 4, you can use the isentropic formula between the state 3 and state 4. So we have to find this T4 first. T4 over T3 will be equal to V3 over V4, right? So you will get A minus 1. Okay, the problems here, we don't have our V3, we don't have our V4. Okay, so what we are going to find here is you can use V3 over formula using the multiplication product rule. Okay, where is my OneNote? Okay, what happened? Okay, to find the V3 over V4 multiplication product rule. Okay, so you put it here V3. V3 can relate to the V2 because it just adjacent to the other, sebelah-sebelah je. So kat sini V2 over V1 and this one is V1 over V4. Okay, jadi if we cancel off V2, we cancel V1 and V1 here, we still get the V3 over V4, the same product as here. So this is what we call it multiplication product rule. Okay, so right now we have the V3 over V2, which is the cut-off ratio that we calculate here. This is I put another pen. Okay, this is cut-off ratio, and V2 over 1 is the compression ratio, and V1 over V2, which is V4 equal to V1, so it will be the same, so it just number 1, so times 1 lah. Okay, like that. Okay, so V3 over V4 will be equal to cut-off ratio. This is the value that we already found, 1773 over 953 over 30. RV is 18, but here it a reverse. This one is the reverse of RV, so you have to put 1 over 18, and V1 equal to V4, so V1 over V4, since it has the same formula, the same value, so let's say lah I put it 8, so 8 over 8 equal to 1, right? So how about if 88 over 88, because it has the same value, they have the same value, so it always get number equal to 1, so you just times with the number 1s here. So finally our V3 over V4 will be 953.30 times 18. So I just leave it as here, 1773 over 17159.4. Why I left just like this form? Because you are going to formula that. So if you round off too early here, the T4 there will get the answer very far off compared to the answer scheme lah. Okay. So T4 over T3 will be 1773 over 17159.4 K minus 1. So our T4 will be T3 is 1773 times 1773 over 17159.4 0.4. So your T4 will be 715.14 Kelvin. So that's our answer for the T4. And how about the pressure? Okay, you can use similar methods here. So P4 over P3. Why we can use the formula? Because the state 3 and the state 4 is isentropic process, so you can relate P4 and P3 using the isentropic formula like this lah. So V3 over V4 power of K. So P4 will be P3 6291.79 times P3 over V4, this one. This one 1773 over 17159.4, the power of K 1.4. So your P4 will be 262.22 kPa. Okay, so we already solved our pressure and temperature. So I put it here T1 300 Kelvin. I just list down to make it convenience lah for us when we want to get that value. So T2 is 953.30 Kelvin, T3 is 1773 Kelvin, and T4 is 715.14, and P1 is 110 kPa. P2 is 6291.79 kPa. So P3 also the same, 6291.79 kPa. And finally our P4 is 262.22 kPa. So that's your answer for the question A. And for the B, okay, so I just move it up there. For the B, we have to find network output, which is W net lah, in unit of kilojoule per kilogram. So our W net is equal to Q in minus Q out. Okay, beware here, be careful. The Q in for the diesel is between 2 and 3, right? This one is the Q in. So this one is the constant pressure. So you have to use the CP for the Q in. Don't use the CV because for the diesel we have the constant pressure there. So we have to use the CP, T3 minus T2. And for the Q out here, this is the constant volume. So we have to use CV T4 minus T1. So our CP is 1.005. The CP is already given in the question lah. Where here CP and then CV. So T3 is 1773 minus T2 is 953.30 minus CV 0.718, T4 715.14 minus T1 is 300 Kelvin. So your final answer for the W net is 5 to 5.73 kilojoule per kilogram. So that's your answer for the B. And for the C is to find the thermal efficiency. Biasalah, wajib ada ni thermal efficiency. Is equal to W net over Q in. So you already have your value for the W net, 5 to 5.73, and now you have to find the Q in. So we just use this formula lah. 1.0051773 minus 953.30. Okay, so I just put the symbol here. This is the Q in and this one is the Q out. So your answer will be minus 100%. So you will get 63.82%. Okay, and finally our D is mean effective pressure. MEP, simple PM, is equal to W net over V1 minus V2. Okay, so to find the V1, you have to use the PV equal to MRT. Okay, so P1, V1, picture 1. So V1 equal to RT1 over P1. So R is 0.286. How do we get the 0.286? You can refer to the questions here. 287, so use 287. Okay, times the temperature 1, 300 Kelvin, and our P1 is 110. So you will get the V1 0.7827 meter cube per kg. Okay, for the V2 you can use the same things. V2 equal to RT2 over P2, since we already have the pressure 2, right? You can use this formula, same thing. Pressure 2 is which one? 953.3 over P2 is not 6291.79. So your V2 will be 0.286 0.0435 meter cube per kg. Okay, so we substitute into this formula. So our PM here is 525.73 over P1 0.7827 minus 0.0435. So your mean effective pressure will be 711.21 kp. Okay, so this one you have to find the V2. Okay, another one is I already show you in the previous examples. We don't have to find the V2, we just manipulate this equation using the RV, because RV equal to V1 over V2. So from I put alternative methods here. So our PM, effective pressure, not the Prime Minister. So V1 will be V2 equal to V1 over RV. Okay, so you substitute this one, so you will get V1 over RV. So the same, we just have to find the V1 only. So it may cut a little time lah, so make it you faster to find the PM. So this is just another method. So W net 525.73 over V1 0.7827 minus V1 0.7827 over RV, which is 18, right? RV is 18. Okay, so the answer should be the same as this one. So let's try. Okay, so I get 711.20 kilopascal, just 2 decimal places off, so it is also correct lah. Good. So that's all how to answer the diesel engine equation. And final chapter here, subchapter here, is the dual combustion cycle. So this is the final piece. After diesel, we already have another version that they combine the dual, means the auto plus diesel. So during the heat addition, there are two processes. One is the constant volume, this one between 2 and 3, and another one is 3 to 4. Okay, so instead of the diesel, we only have straight constant pressure, and for the auto we only have constant volume. So why not we combine those two concepts? So as the outcome, we have the dual combustion cycle. Okay, so the difference here is the Q in. You have to find two Q in. One is between the CP T4 minus T3, and other one is the Q in between 2 and 3. So this one Q in, you have to use the CV because the constant volume kan, between 2 and 3 constant volume, between 3 and 4 is constant pressure. So yang Q in yang kat sini, you have to use T3 minus T2. So that's why you have two types of Q in. So you have to combine everything about the Q ins here. Ni between ni constant volume. This one during the constant pressure. Q out still the same. You have to use the CV because the constant volume between 5 and 1. Okay, how about the excellence here is the pressure between P3 and P2. So we have another ratio there, excellence. Okay, so that's all. I will show you example of the dual cycle. So after this, you have to do tutorial. Okay, I already put in this in this slides in this OneNote under the tutorial here. So you see that the past years questions, most of the time they ask about the dual cycle. Let's see here, December 2019 dual cycle, December 2018 dual cycle, June 2019 dual cycle, January 2018 dual cycle, and June 2018 diesel. So most of the time is dual cycle or diesel. So focus more on the dual and diesel lah. Okay, I will show you the final example here, March 2017. After that, we officially finish our lecture of this MEC251, and you can focus on doing your exercises. And I mentioned you many times before, to score MEC251 you have to do a lot of exercises, to do a lot of past years questions. Okay, so let's try this March 2017 dual combustion cycle. Okay, so let's read the question for March 2017. Okay, dual combustion. So you have to draw the PV diagram look like this. Because of the dual cycle, we have two process that use the constant volume here and the constant pressure here. Okay, so the Q in here happen between the 2 and 3 and also 3 to 4. So this is the Q in and this one is also the Q in. Okay, let's continue. Has a compression ratio of 13. So this is the RV, which is the V1 over V2 equal to 13, and use air as the working fluid. At the beginning of the compression process, okay, at the beginning of the compression process, this one lah, before it compress, state 1, the air temperature and pressure are 37 degrees C. So at the beginning of the compression means this is the state 1. So 37 is T1, 160 is P1. Okay, respectively. Heat addition process take place until the cycle reaches maximum temperature of 1900 degrees C. Okay, so you see that the temperature is the highest after the Q in. So means the T4 here is 1900 degrees C, and produce the total heat of 1250 kilojoule per kilogram. So this is the Q in total. Okay, means that the value given here is equal to Q in during the CV and the Q in during the CP. So you total up, you get the 1250 kilojoule per kilogram. Okay, so sketch the cycle on PV diagram. I already sketched here. So after that, you have to write down the state 1, state 2, state 3, state 4, and finally the state 5. Okay, you write down the process between 1 and 2. Going 1 to 2 is isentropic. 2 to 3 is the constant volume, constant V. So 3 to 4 is constant P, constant pressure. And finally 4 to 5 is isentropic again. And 5 to 1 constant volume. Okay, so we wrote down everything. State 1 we have temperature 1, 37 degrees C equal to plus 273, so 310, right, Kelvin. So our P1 is 160 kPa. After that we have the RV, which is V1 over V2 equal to 13. And then we have the temperature at state 4. This one, the highest or the maximum temperature is after the Q in. So here lah, T4 equal to 1900 degrees C. And the total, so you put it, it's okay if you want to write down under state 3 or the state 4, but make sure you know Q in total is equal to Q in 2 to 3 plus Q in 3 to 4. We have two processes that contribute to the Q in. Okay, so equal to 1250 kilojoule per kilogram. I put here lah, between state 3 and state 4. Okay, so I think that's all the information that we have. So let's start with the state with the most information. So we start with the state 1 and state 2. So I write down using the black ink. Okay, state 1 and state 2, it is an isentropic process, so you can use this formula, T2 over T1 equal to V1 over V2 to the power of K minus 1. So we have to find the pressure also at every state. Okay, so another formula is you can use the P2 over P1 equal to V1 over V2 to the power of K. Okay, so these two formula for the isentropic process. Here we can find the temperature, here we can use to find the pressure. So we use this first to find the temperature first. So the T2 will be equal to T1 310 times V1 over V2 is 13, our compression ratio, and then 0.4. So our T2 will be wait a second. Okay, 310 13 0.4. So I get 864.8465 Kelvin, and P2 is equal to P1 6 0, V1 over V2 is 13 1.4. So you will get 5802.8411 kPa. That is our P2. Okay, and then for the state 3, it is the constant V. So V3 equal to V2. We can use this formula that is already given and value on 250. So just write down Q in 2 to 3 is between the volume constant, so you can use the CV T3 minus T2 plus, okay, Q in here is between 3 and 4. This is the CP, so you must use the CP there, T4 minus T3. Okay, is equal to 1250. So we write down here CV is 0.718. T3 we don't have yet. T2 we already have 864.8465 plus CP is 1.0005 already given. T4 we already have 1900 equal to change to the Kelvin unit, 2173 Kelvin. So 2173 minus T3. Okay, so the unknown value here is only T3, so we can find the T3 using your simultaneous equation lah. So okay, I will show you every steps here. 1250 equal to 0.718 T3 minus, I see, 864.8465 620.9598 plus 2183.6.865 minus 1.005 T3. So here we okay, rearrange this equation, so you will get here positive to the left side will be negative 865, and then 0.718 minus 1.005, so you will get negative 0.287 T3. So I put a bracket T3 there. So 1250 plus 620.9598 minus 2183.865, you will get minus 312.9052 equal to negative 0.287 T3. So your T3 will be 1090.262 Kelvin. So now we already have our T3. Okay, how about the P? P3 is equal to P4. So we can KIV first. We can find the P4 here. Okay. So I list down here lah. T1 equal to 310 Kelvin. T2 equal to 864.8465. T3 is 1090.262 Kelvin. Okay, and for the time being we have P1, P2, okay, and P3 we don't have it yet. Okay, so let's go to the T4. We already have the value T4 2173 Kelvin. Okay. Okay, so we have to find the P4 and T5 and also pressure as T5. Okay, so let's go to the state 4 and state 5. Because it is isentropic, we also can use the formula of this one. So T5 over T4 will be equal to V4 over V5. Is it correct? Yes. K minus 1. Okay, and T5 will be equal to T4 2173 V4 over V5. K is 1.4 minus 1 is 0.4. So the problems here is to find the V4 over V5. We can use the multiplication or product rule. V4 over V5 equal to, we start with the V4 with the V3, and then V3 with the V2, and then V2 with the V1, and then V1 with the V5. So if we cancel off everything here, V3, V3, V2, V2, V1, V1, we still get the V4 over V5. Okay, so V4 over V3, we cannot get that, but we can refer to the ideal gas equation, which is P4 PV 4 over RT4 equal to P3 V3 over RT3. So we can cancel off R, and then between 4 and 3 you see that there is the constant P, so we can cancel off P. So you will get V4 over T4 equal to V3 over T3. Okay, so we rearrange temperature with the temperature and volume with the volume. So you will get V4 over V3 equal to T. Is it correct? V4. This one goes the T4. Okay, is it? Okay, is it correct? It's correct already. Okay, T4 over T3. Okay, this goes up, V4 over 3. This goes down, V3, V4 over V3. Okay, so T4 over T3 is 2173. This one 2173 over T3 is 1090.262. So we already have V4 over V3 here. And for the V3 over V2, V3 and V2, it has the same volume because the constant volume. So this one will be equal to 1. Okay, 1 only. And for the V2 over V1 is reverse of the RV. Yeah, so this one is 1 over 13. And V1 times the V5, you see there, V1 and V5 is also the constant V, so it will be 1 there. So finally we can get our V4 over V5 equal to this one. You get this value 2173 over 1090 over 26 T3 262. Okay, times this one is 1 times this one is the reverse RV, so 1 over 13, and this one is 1. So V4 over V5 will be 2173 over, okay, I have to use my calculator here, 6262 times 13, so you will get 14173.406. Okay, so substitute into this value and this equation, so you will get T5 equal to 2173 so our T5 will be 1026.3463 Kelvin. So I put it here 1026.3463 Kelvin. Okay, so and then we also have to find the pressure, right? Use the same method. P5 over P4 equal to V4 over V5 to the power of K. So P5 will be P4, we also don't have yet. But V4 we are this one. Okay. So P3 equal to P4. If we want to find the V5, P5, we also can try the alternate, which is we can relate state 5 with the state 1. Okay, we use the PV, P5, V5 over RT5, P1, V1 over RT1. So R we cancel off. Okay, and then between the V1 and V5, the volume is constant, so we can cancel off volume there, and then P5 will be equal to P1, T5 goes up times with the T5 over T1. So we already have the P1, right? 160. So you will get 160 times T5, this one, 1026.3463 over T1 is 310. So our P5 will be 529.7271 kPa. So put it here, 529.7271 kPa. Okay, and then so this formula here, we don't have to find the P5. We have to use the P5 value to find the P4. So here we rearrange back to get the P4. So P4 will be P5 over this one, 2173 over 14173.406 power of 1.4. So our P4 will be 7315.3059 kPa, and then put it there, 7315.3059 kPa. And finally, because of the state 3 and the state 4 have the same pressure, so P3 also 7315.3059 kPa. So you already go halfway there after you get all the temperatures. Okay, so this is the question A, and the question B is the word net output. It's just the easy one. Word net is Q in minus Q out. So we already have the value of Q in, total 1250. But the Q out we must have calculate first. The Q out here is between 5 and 1. So and it has the same has the constant volume, so CV T5 minus T1. So you will get CV is 0.718, T5 1026.3463 minus T1 310. So you will get the W net is 735.6634 kilojoule per kilogram. And the C is thermal efficiency. Okay, thermal efficiency is W net over Q in equal to 735.6634 over Q in. Q in is already given here, 1250 times 100%. So you get 58.85%. And D, Okay, this is the cut-off ratio. Basically, the cut-off ratio is between the constant P process. So it is the V4 over V3. So the value here, V4 over V3, this one. So the V4 over V3, we already have obtained that value. Because if we don't have that cut-off ratio, we cannot solve the temperature 5. So we just write down back here lah. V4 over V3 is 2173 over 1090. Sorry. Betul lah. 0.262. Okay, that's our answer. And finally, mean effective pressure, right? Okay, so MEP equal to W net over P1 minus P2. So we can use W net over V1 minus since RV equal to V1 over V2, so our V2 is equal to V1 minus RP. So we put it here, we substitute back, so V1 over RP. So our W net 735 0.6634 minus over, sorry, V1 minus V1 over RP. Okay, so to find the V1, we can use the V1 equal to RT. So V1 equal to RT over P1. So you will get R is 0.287. P1 is 310 and P1 is 160. So our V1 is equal to 0.5561 meter cube per kg. So put it there, so you will get RV value is 13. Our EP mean effective pressure is 1433.14 kPa. Okay, so that's the answer. See here, there's a lot of calculation that you have to do, and if you don't familiar with the techniques and methods here, you will have difficulty during your test and your final exam. Oh, sorry, this chapter we only be in the final test, so there will be no internal combustion engine in the test 2. Test 2 only cover the Rankine cycle and the Brayton cycle only. So internal combustion engine here will be asked in the final test only. Okay, so that's all for our final chapter, and I hope if you cannot catch up all the things that I cover for in this video, so you can pause and you can continue, you can learn by your own pace. So don't rushing here. Use this video accordingly. You can learn, depends on your pace and your efforts lah, but make sure you try every examples here that I have already demonstrate here. Okay, so that's all. Hope you can learn everything from this video, and if you still have the problems, you can ask me in the WhatsApp group and we can discuss later. Sorry, I cannot do the live lecture for this topic because I have a personal matter to do during the Monday class. And that's all. Assalamualaikum and bye bye.